So there's an example here. Again, these are all taken from your textbook. It asks you to write a test program for the PIC 18 chip to toggle all of the bits of port B, C, and D every quarter of a second, assuming a crystal frequency of 4 megahertz. Okay, so in this case, you're going to pop open MPLAB and test this looking at the using the simulators. You're not gonna use a piece of hardware for this. You're going to use the simulator within MPLAB. So as you go through and set up a file, instead of choosing PIC 18F458, go ahead and choose your 4520 and set up your file, just like I showed you in the MPLAB X IDE tutorials. And then enter the information. Get used to entering this information and testing it, and see if it in fact works. Okay, the idea here is that we want to go ahead and check in the watch window that each of these steps does exactly what it is supposed to, and that you can see it as it's progressing, and you'll have to use um, the step in function within MPLAB to do that. Okay, I/O bit manipulation, powerful and widely used within the PIC family. In this section, we'll further examine the PIC 18 I/O instructions, I/O ports, and bit addressability. So now we're going to get to where we can look at things where we can access 1 or 2 bits of the port instead of the entire 8 bits. And sometimes that's key. We just want to see what's going on in 1 or 2 bits rather than everything that is in a particular file register. So we've got some new commands, instructions here that we need to learn. Sometimes the need to access only 1 or 2 bits of the ports, but not all 8. It's a powerful feature of the PIC I/O, and it's their capability to access individual bits of the port without altering the rest of the bits. So we're going to look at something called single bit or bit-oriented instructions. These instructions are abbreviated BSF, BCF, BTG, BTFSC, BTFSS. Okay, and as you get used to these, you'll understand what's going on. In this case, we're looking at file registers and a bit location. So you would identify the file register and the bit location. In this case, BSF, bit set file register, sets the bit to 1. That was BSF. BCF, bit clear in a file register at a specific bit, sets it at 0. If we want it to toggle, it'll basically do a complement. So it's going to complement that bit. So you can see we're doing things at the bit level and not at the 8-bit level. BTFSC, bit test file register, skip if clear, so we'll skip the next instruction if there's a 0. And then the last one, BTFSS, will do a skip if it's set or if it finds a 1 at the location. So these can be very important and very useful tools if you're looking at making changes or determining what's going on at a particular bit level. Sometimes as we look at this on a port by port basis, it becomes a powerful feature for the PIC I/O for its capability to access then any one of these values, individual bits of the port, without altering again the bits to that port. So we've seen this before. The particular port, this should say port A. Let's put that in there. It's going to, there we go. So at port A, you notice we've got 6 ports. Port B, we actually have 8 ports. 8 ports, 8 ports, 8 ports. And again, as we said earlier, port E, we had only 3. Okay, and port bits, then D0 through D8. Okay, so those become very important values to us. So if you take a look in your text, the information about each of those instructions, the BSF bit set register to set high a single bit of a given file register and location. We use the syntax then BSF and then follow it by the file register and then whatever the bit number happens to be that we are looking at operating at the bit level, where the file register can be any location of a file register and the bit number is the desired bit number from 0 through 8 because we're dealing with 8 bits. Although the bit-oriented instruction can be used for manipulation of bits D0 through D7 of any file register, they're mostly used for I/O ports in embedded systems. So as an example, here we have the bit set file. Port B is the register and the bit number 5. So in this case, it sets high bit 5 of port B. Okay, if we take a look at this little example here, we can see that we're looking at an LED connected to each pin of port D, and it asks us to write a program to turn on each LED from D0 to D7. Call a delay module before turning on the next LED. Again, if you didn't put the delay in there, you probably won't see it. You're not gonna have a board that you can work on, but you can certainly see this. Go ahead and enter this code into MPLAB and watch to see what happens using the watch window, because you will see the states change on each of the ports. Bit clear, again, the same thing is going on. Now instead of setting, we're clearing a particular bit. Okay, so to set a single bit of a given file register high, we're going to use the command BSF followed by the file register. In this case, it could be port B, bit number 5 sets high bit 5 on port B. Okay, the clear, just the opposite of the set there. Again, the syntax is the same here. Now the abbreviation becomes BCF. It'll do the same thing. Any file register, any file bit number from 0 to 7. Must activate the appropriate bit of the tri-state register to reflect changes on the pin. Okay, we got again another little example here. Write a program to create a square wave of 50% duty cycle on bit 0 of port C. 50% duty cycle means that the on and off states, or high and low portions of the pulse, have the same length. Therefore, the toggle at port RC0 with a time delay between each state. So again, take this code, put it into MPLAB, and test it and see what it does. You can see down here they've streamlined it by reducing some of the instructions, but you end up with what would be the same duty cycle. Okay, same example. This one they're asking you to create a square wave, 50% and 66%. Another way of doing the same program, and then the example on the bottom is at 66%. The bit toggle, now instead of it changing the state 1 or 0 that you've identified, in this case it looks to see what was there and changes it to its complement. Okay, and we can see here again another little example of the way that works. Notice that RB2 is the third bit now of port B, where the first bit is RB0, the second bit RB1. In the table, we can see this example 4.2, for example, of the manipulation. So in this case, we are going to toggle the bit that we're looking for in the exercise, in this case bit 2. Checking an input pin to make decisions based on the status of a given bit. In a file register, we use instructions BTFSC, bit test, file register, skip if clear. So we're doing a little test in here. We do a bit test to determine what the current status is. If it's a 0, it skips this instruction. Okay, in the other instruction BTFSS, it would skip if it saw a value at that particular bit. Okay, so we can see here the layout. Use it to monitor the status of a single bit for a high in this case. The clear, doing the same thing, but now if there's a clear there, we use the monitor to monitor the status of a single bit for a low indication. Got an example here that we can take a look at, and you can see we've got our set and clear values. Right here we've got our skip if set value. So if it saw a high there, it would skip that step and move on with the instruction. So in this program, the BTFSS port B2 stays in the loop as long as RB2 is at a low. When RB2 becomes high, then it skips the branch instruction to get out of the loop and writes the value, in this case 45H, you can see up here, fourth line, to port C. It also sends a high to low pulse to RD3. Okay, and we can see that down here on the last two steps. The skip, if clear, our example here, assume that the bit RB3 is an input and represents the condition of a door alarm. If it goes low, it means the door is open. Monitor the bit continuously. Whenever it goes high, send a high to low pulse to port 5, which sets off a buzzer. So this is a practical application of a simple little door alarm, checking the condition of the door and sending a signal to sound the buzzer. Can also use the bit test instructions to read the status of a single bit and send it to another bit or save it. Okay, and here's a quick little example of that. Go through the code, again test it in MPLAB, and look at those values as they change in the watch window. We can go through that example. It's always a good idea to look at your flow charting here and check to make sure that the logic makes sense. Do we have our decision points set right, so that depending on what is set, in this case if it's a high, does it jump or does it continue through the process? Okay, another program from your text. This is got a set clear in this instruction set. Again, check out the flow chart. Make sure that the logic does in fact make sense for executing your program. Reading a single bit, then you can use the bit test instructions to read the status of a single bit and send it to another bit or save it. Okay, so you can see here we've got a switch connected at a port and an LED. Write a program to get the status of the switch and send it then to an LED, whether to light it or not. Again, a switch connected to a pin RB0. Write a program to get the status of the switch and save it in DO of the file register location. So in this case, we're just saving the value rather than making it do something like turn on a light. Reading input pins then versus a latch at a port. In reading a port, some instructions read the status of the port pins while others read the status of an internal port latch. Remember, latches set and they don't change unless something else causes them to in fact change their levels. Okay, you can see here again, we've seen this diagram several times. The latch register role in reading a port or a latch. And you've got a couple of latches here, a data latch and a tri-state latch. Depending on what information has gone to the latch, we'll make it either hold, or set, and or clear. In reading latch reports, some instructions read the contents of an internal port latch instead of reading the status of an external pin. Okay, in this case we've got our complement F port B. It's a sequence of actions here. The instruction reads the internal latch of the latch B and brings the data into the CPU. The data then is complemented, so if it's a 0 it becomes a 1, if it's 1 it becomes a 0. The result then is rewritten back to latch B. The data on the pins then is changed only if the tri-state value, the tri-state register B bits are cleared as 0. So it's holding or accumulating our values to make some decisions in what to do next. In reading latches for the ports, you can see here that some of the read, modify, write instructions used, adding our functions here for setting or clearing the complement or an increment, subtracting, or doing an exclusive OR are all instructions that are used in read, modify, write executions. So what we've done in this chapter is we've focused on just the I/O ports of the PIC. The 5 ports of the PIC 458 were looked at, port A, B, C, D, and E. The ports then can be used for input or output. Don't forget, you have to set them, you have to determine them. All ports have alternate functions. 3 registers associated with each port are the port, the tri-state, and the latch. Their role in I/O manipulation was looked at, then I/O instructions for the PIC were explained. Numerous examples were given. Go back and take a look at those examples. Make sure you understand why a specific instruction was used and why the logic and the flow was done the way it was. And then finally we looked at the bit addressability of the ports. Very important in a PIC microcontroller.